very interesting panel this evening. Got it.
You're live.
Oh, great. Thank you, Grace. Okay.
All right, saludos everyone, and welcome to our salty solar system. My name's Edgard Rivera-Valentín. I'm a planetary scientist at the Lunar and Planetary Institute, and the convener for the conference that just finished, which is Modern Brines. It is part of the Brines Across the Solar System conference initiative that the LPI is putting together. Tonight, we're going to be talking with our panelists about what they've learned at the conference and also answering your questions about brines. But first, here's my co-host, Andy.
Well, on my screen, I'm above you, but whatever.
Oh.
I am Andy Shader. I'm a senior education specialist at the LPI. I work with Ed, sometimes too closely, but it's still fun. I'll be a co-host with you all this evening. So welcome. Thank you for joining us.
Thank you. And today we have a great panel. Let's start getting to know them. First off, Kennda.
Hi, everybody. My name is Kennda Lynch. I am a staff scientist here at the LPI. I am an astrobiologist and a geomicrobiologist, and I study extreme environments as analogs for paleolake basins, hypersaline paleolake basins on Mars. What else? Was I supposed to say one other thing? Okay.
That's perfect. Next up, we have Sean.
Hi, everyone. My name is Sean O'Hara. I'm a postdoctoral fellow at the LPI. I'm a geologist and a geophysicist by training. So I study the deformation of the crusts of both icy bodies in the outer solar system like Pluto, and more recently, like Venus volcanics.
Thank you. And now we have Mohit.
Hi, my name is Mohit Melwani Daswani. I'm a scientist at the Jet Propulsion Lab in Pasadena, and I study water-rock interaction on ocean worlds, including Europa, and also a bit of Mars.
Thank you. Up next, we have Jen.
Hi, I'm Jennifer Hanley. I'm a planetary scientist at Lowell Observatory. I study the stability of liquids across the solar system, primarily through experimental techniques, simulating the conditions in the lab, as well as remote sensing to understand where salts are and how they affect the habitability and stability of liquid water across the solar system.
Thank you. And finally, but definitely not least, Abel.
Hi, I am a planetary astrobiologist at the Planetary Habitability Laboratory at the University of Puerto Rico at Arecibo. I study the theory behind the habitability of Earth, the solar system, and exoplanets. I also use the Arecibo Observatory to study the activity of red dwarf stars with planets.
Thank you so much. Now, before we begin, let's get rid of one jargony word that you see in this title, and that's brines, right? Brines across the solar system is the thing that we're studying, but what is a brine? You may have heard the term when you're making your turkey, right? Put water and salts together and put the turkey inside there, you're brining your turkey. Although in science, brines in some fields can have a certain definition, like a certain amount of salts, then that liquid becomes a brine. Really, we're using this word here just to mean anytime you have liquid water plus some amount of salt. So the ocean, the sea, all of that can be a brine. If you do your little gargles with some water and some salt and take it back, that's a brine. That's what we're talking about here.
And when you pickle things, right? Make pickles.
And,
Yep.
And when you pickle things.
Yep.
Andy?
Sorry, how the wind's so nutty. Yes, thank you, Ed, because that's what, yes, that brines, what does that mean? Well, thank you all for those examples. And so, but what is it that makes, why this meeting now, right? I mean, as far as I know, this is a relatively new, if not the first time something like this has been held to cover these topics. So why now?
Why now? It's a really good question. So behind me, This way. Behind me, you see a bunch of different planetary bodies, right? Mars, Europa, Enceladus. Then you also see like a little comet over there. One of the things that we've found as we've explored our solar system is that every now and then when we go somewhere and we're like, that's gonna be a cold, dead world. We get there and surprise, there's a brine, like when we went to Ceres and we thought it'd be looking like any other asteroid, but no, it didn't. So Ceres is a main belt asteroid. We also have evidence that Mars had a bunch of water on it in the past. There's evidence that maybe today it could host. We also have all of these icy moons from Jupiter out to Saturn and beyond that might actually be just balls of water with an icy cap on top of it. So we're studying this now because we're seeing brines everywhere. So let's all sit down and talk about it and really understand what's happening. Why do you all think brines are important to study right now? Why don't we start off with Kennda?
Well, just as you said, we have these amazing worlds out there that are super far away from the sun, but yet because of these brines, they have liquid water. And wherever you have liquid water, you have a possibility of life, because life as we know it for now needs liquid water to do chemistry. So we need to understand, brines and how they keep this water liquid and what that means for how habitable that liquid water is on those different planets, so we can try to understand if life could arise or could be sustained on these other worlds. All of a sudden, we have these potentially habitable worlds that are outside of our Goldilocks zone, which is what we usually consider our habitable zone around a star where we think liquid water can form. Well, we have this whole new definition of how liquid water can form because of these brines. And it's really important to understand that so we can understand if life can live on those planets.
Definitely, thank you. Mohit?
Well, I agree entirely with what Kennda said. So I just wanted to chime in that brines have the potential brines lower the melting temperature of water. So that allows liquid water to stay stable under low temperature conditions. And that allows liquid water to exist further out in the outer solar system, further out than what we had expected. And so that may allow life to exist in those environments. So that is why I think it's important.
And I think too, right, why now? We're getting ready for a lot of upcoming NASA missions that are going to study a lot of different planetary bodies. Of course, we have a lot of missions on Mars or, orbiting Mars right now, but we also have the upcoming Europa Clipper mission, Dragonfly, which is maybe not quite brines, but it's an ocean world. And then, potentially even further out into Uranus or Neptune systems. And so I think that we're kind of in a really great place to study brines right now because we've seen brines. We kind of have a pretty good understanding of what's happening on Mars, and we want to maybe expand that to subsurface and also outer solar system bodies.
Definitely, thank you. All right, Andy, do we have questions from the audience?
There actually is a question that came up in the chat box. And just real quick, if you do have a question out there, please feel free to type that in the Q&A option that you can type your questions into, and we can get to those live, or maybe even just answer them right there in the box for you. The question we do have actually goes back to where we're talking about what a brine is. And this question is, does a brine have to involve sodium chloride and water?
Great question. I'm going to throw that to Jen.
Yeah, it actually does not have to include sodium chloride and water. It does have to include water, but when we talk about salts, there's lots of different salts. Sodium chloride is the one that most people, I'm sure, are familiar with. That's what is predominantly in Earth's oceans. It's also called halite. It's table salt is what we use. But there's lots of other salts that you all are probably familiar with as well. You might have heard of Epsom salt, use it for your baths. That's another kind of salt. That's magnesium sulfate. There's also salts that we use to de-ice roads in the winter, and that's typically a combination of magnesium and calcium chlorides. So there's lots of different types of salts, and they all affect water in slightly different ways. And so that's one of the really cool things about this conference is we talked about how different salts affect water in different ways. And so different salts lower the freezing point by varying amounts. And so understanding exactly which salts are present across the solar system, where they are present, in contact with what amounts of water, is all really important to understanding these brines and the habitability.
Perfect, thank you. Kennda?
I was just going to say there's another question that could follow right onto this. Ronald asked, can water be too salty for life? And the answer is, it's not necessarily about how much salt there is. It's a matter of what the salt is made up of. Just like Jen said, there could be lots of different types of salts. And certain salts, once they get over a certain amount, if there's a certain kind of salt, especially like, for example, magnesium salts, if there's certain salts that get over a certain concentration or amount of salt, then it can start to give life problems. But it kind of depends on what kind of salt we're talking about, then how much is there. It kind of determines whether or not it's going to be too much or too hard for life to live in. But you'd be amazed. There's some life now that can only live in really high concentrations of salt. It doesn't know how to live. Once it goes below a certain concentration of salt, it freaks out and is like, where's all my salt? I need it. So it's kind of interesting how life adapts to living in this kind of extreme environment.
And actually, to follow that on, there is another question that says, what is an organism that could survive in brine?
Oh, those organisms are called halophiles. And there's so many different kinds of organisms that are halophilic and that they love to live in salt. My favorite one, and I'm forgetting the actual name of it, is an extreme halophile that's actually got a square shape. It's actually kind of a square in shape because it's designed itself to be able to survive in extreme salt environments, and so it's changed its shape to kind of improve its integrity. And so it actually looks kind of almost like a blobby square. And I forgot the name of it. I can look it up for you, but it's one of my favorite microbes.
Awesome, thank you. Andy, other questions?
Nothing online yet. So keep them coming though, if you got them. So what is one new, we'll go around to everybody here on this. What's one new thing you learned this week during this meeting? We'll start with Mohit.
So I learned a lot this week. It was a fantastic workshop. So thank you very much to the organizers. If I had to choose one single thing, it's tough, but I've been thinking about the, moving on sort of to the technical bits, the confinement pressure within porosity, nanoporosity affects the stability of liquid water. I hadn't given that much consideration before, but that seems to affect whether liquid water or whether water will remain stable at under different planetary conditions. So that in addition to salts can mean that we can even lower the temperature further before water will freeze. So I wonder, how that affects our understanding of how water can stay stable within planetary bodies. That is one thing that I learned and will need to think about.
Thank you. Abel, we haven't heard from you in a bit.
Yes, there are many things we learned this week, but I am particularly intrigued by a discussion today about the Europa, the Enceladus jets. If you are trying to sample these jets of material coming from this moon, from Saturn, then you can do it from space. But I always thought that these jets will be taking all the material away from the moon, more than the escape velocity of the moon. But some of that material could fall back. So if you put a lander close to one of those jets, you will have a complete history probably for millions of years of different layers of the material coming out. And that will be an amazing place. Just the material is there concentrated for a long time. And I think that's one of the things that I would love to see in the future, a mission to one of those jets.
I agree. That's going to be awesome. Sean, how about you?
One thing I learned is that I definitely got to start paying more attention to series. Usually in my work, the direction I've come at brines from is usually we see some kind of strange geologic feature that we don't necessarily understand how it got made, or maybe we have an intuition of how that kind of feature could be made on Earth, but it would require liquid water in that case, something like slumping landslides or like volcanoes, or some kind of, you need some kind of fluid in order to make it work. And so we see that and we say, okay, well, maybe brines were involved. Maybe there was, you just use this big blank piece of paper that says brines on it, and we put it over that and then go from there. And the really exciting thing that I saw in this conference was just the level of detail that's coming out of the work on series in terms of exactly which brines are affecting the surface in which ways. And there's different, you can have different fractional crystallizations of brines, certain brines freezing at different temperatures to other ones. And that you're going to be able to see that in the geology and see that in not just in the surface chemistry, but also potentially in the different types of landforms and when they formed. And that's a huge area for being able to interpret the history of individual places on these bodies. That is just, being able to build up that body of intuition is really huge.
I agree, definitely. Series is super cool. I like asteroids. I like brines. Brines and asteroids. What? That's just super awesome.
I think Ceres goes by the name dwarf planet now, not asteroid.
Ceres is a dwarf
not
planet.
a dwarf.
Even though it's
it
in
is
the
a
belts.
pretty body. So how about you, Jen?
I, like Mohit, really learned a lot this week. It was just such an engaging and interesting conference. But the thing that really sticks out for me is a lot of the astrobiology stuff and looking at how different organisms survive in different salty conditions. But in particular, the one about the nematodes was just so neat to see that they can survive in the Great Salt Lake and in these really salty places that we haven't seen them there before. And so I thought that was really kind of a really fun takeaway for me from this conference.
Super cool. And Kennda.
So I'm gonna have to agree with everything I've heard so far. Series is really cool, and it's got my mind thinking about this whole idea of sloshy cold mud and how, briny sloshy cold mud. How can we figure out how life can live in it? And I'm just kind of really excited about that thought. And then, I agree with Jen that one of the big things that really did stick out to me is just the level of detail of how we're trying to understand the actual physiological processes of how different microbes figure out how to live in different kinds of environments, even if we're just doing it in the lab. And then how the coalescence of all that information, together will really help us try to understand how to start thinking about what a brine-based ecosystem on another planet could be like. Once we pull this information together, we understand how these bugs can react to different kind of conditions. We study them in these natural brine environments, and we pull all this information together along with all of the different dynamics of how the brines form, how they take on water and deliquesce, or how they precipitate, all these pieces. And being able to pull it all together, I can just see that, you know, we're at a point where we're going to be able to come together in community and really bring all this information together and kind of help us really kind of lay out like definitions and you know, kind of start putting pieces of the puzzle together about what these kind of environments could look like on some of our these other you know, briny planets.
I want to add something that I tell my students that biology is more complex and more difficult than physics. They don't believe me, but I have to stress out that when you're taking biology, there's so much that all your bachelor degree is probably the introduction. You don't get to the math. And most of that math is so complicated that we don't know yet. It's amazing that we have equations about our universe, our cosmology, the whole universe, but equations about life and first principles, and we have the life right here in our hands. So there is too much to understand, too much to do in biology, integrated biology, chemistry, and physics that we need to understand.
Definitely agree. Thank you, Abel. Andy, do we have questions now from the audience?
We do. We have quite a few questions, and hopefully we'll have time to get to all of them. But first one is, has salt plus water or brine been found on Titan?
I could probably take that. So not liquid water. Our observations of Titan are limited to radar observations of the surface, so we can see that yes, it's big on radar. So we can see basically the roughness of the surface in various places, and we can know the chemistry of its atmosphere. So we know that the surface of Titan has a lot of solid water on it, solid water ice, and it has a lot of solid organic particles that are either rained out as sand or as liquid. We know, for example, there are large bodies of liquid methane and ethane on Titan, because it's so cold there, you can actually have a standing body of liquid gas, natural gas, basically. But we don't have any evidence so far of water-rock interactions on the surface of Titan. That's something that the upcoming Dragonfly mission, if it's there to be found, they'll be able to find that.
If I remember correctly, doesn't Titan possibly have a subsurface? I think it has a subsurface water ocean that could be brine.
Yes, there. And I should specify, there is most likely a water ocean underneath, but we think the crust is thick enough that it's probably not it probably doesn't interact with the surface very often. But we could be wrong.
Yeah, but it's definitely something that that Dragonfly is going to look for, is to see if there's any kind of surface subsurface connectivity in any way, because that would be very fantastic, especially with all those organic solids, all the organic sands. Very exciting.
Great, thank you, everyone. I got a question here from YouTube. How important might brines have been in the origin and evolution of life on Earth?
I'll take that one. Okay, so prebiotic chemists really like brines for certain processes, especially when we're talking about making things like polymers, like big long chain things that kind of make different structures like cell walls and all that kind of stuff. When we're talking about different kind of reactions, because brines can precipitate and deliquesce, which means they can go from liquid to solid and back and forth and do all these different kind of processes and go from a dry environment to a wet environment. They really like brines. They really like brines for those kind of reactions. They also like brines for other different types of prebiotic chemistry. So brines could be very important for helping to create some of the prebiotic molecules that kind of led towards the evolution of life. So they're definitely an important thing that we look at, and that a lot of prebiotic chemists, they definitely put a lot of consideration into, how do brines, and especially the type of brines, affect prebiotic chemistry.
Great. Thank you, Kennda. Another question here. Did alkali salts, for example, sodium chloride and calcium chloride, condense together with water ice in the early solar nebula?
That's, if you don't mind, I might try to answer that.
Sure.
So that's a really good question. We have some evidence of salts in in chondrites. Chondrites are meteorites. So they're samples of rocks out there in space that have arrived on Earth. And we find some salts in those meteorites. So we heard this week about salts found in the chondrites, Zag and Monahans. They're particular meteorites. They contain sodium chloride and potassium chloride as well. So there's some evidence that these salts would have been present in the building blocks of planetary bodies to begin with. So I think that may answer the question. Yep.
Okay, thank you, Mohit. Another one from YouTube. How do you think the brine is ascending on Ceres' surface? Radioactive elements in the subsurface, residual heat from its formation?
I think those mechanisms still need to be studied properly. And there are various models that suggest, well, maybe there's some form of convection within Ceres' interior. There's this model for Ceres, maybe the interior of Ceres is a bit like a mud ball. And then over time, that mud convects and brings up brines from the deep interior. Another model suggests that maybe those brines are produced in the deep interior to begin with, and then somehow make their way to the surface. So I think it's still something that's a bit of an open question and something that we're actively investigating. But I think a landed mission on Ceres would really help. I think we're all excited about maybe sampling the salts on Ceres, which are carbonate salts and bicarbonate salts. And these are different to most of the salts we've seen on Mars, for example. So I think that'll be quite exciting.
Thank you. And wouldn't a landed mission on every single solid surface in the solar system be awesome? Let's push for that. The next decadal, Ed. All right, another question. Here, this is, I guess, a good one for Jen. Why do brines freeze at different temperatures?
That's an excellent question and something that we really want to understand more. So something that we can understand is called water activity, and it's basically the ability of water to behave like itself. And so something with an activity of 1 means that it's pure liquid water and it's behaving just normal. And if you remember your chemistry, water, H2O, is a polar molecule. And so if we dissolve different salts into the solution, those ions will start to pull on the water molecules. And so different salts have different ionic strengths and sizes of the physical ions. And so all those things work together, in addition to the concentration, of course, to inhibit water from acting like itself. And so if we have a really concentrated salt, for instance, magnesium chloride, and you have this magnesium, which is a 2+ ion, and the chloride, which is a -1, but you have these ions interacting with the water, and it prevents the water from going into the solid phase to freeze. And so different salts, for instance, magnesium sulfate, or if we think about that Epsom salt, that lowers the freezing temperature by only a few degrees. Whereas magnesium chloride, the reason we use it to de-ice roads is because it's 25, 60 degrees reduction in freezing temperature. And so measuring, modeling through modeling and experiments, understanding how different salts affect the freezing point and what happens if you put mixtures together is really important. And that's a great question. Thanks.
Well, thank you for your answer. Appreciate it. Do we know enough, or do we know enough now to compare the brines of Mars, Ceres, Europa, and Enceladus, etc., etc.?
I would say not enough yet. I mean, even though we can go to Mars a lot, we're still just starting to really understand the different potential compositions of the brines on that, that could have been, on Mars when it had, was in a state where it could have had liquid water. And that could be different depending on where you are on the planet Mars. And with Europa and Enceladus, I mean, we've gotten like little whiffs of, kind of what the brine composition can be like. And we've got the modeling from, from the geophysical data. I don't know if I wouldn't feel confident that we have enough information to really start comparing them in any kind of meaningful way yet, but I'll let the other experts kind of weigh in on that.
No, I think that's basically correct. And I think that's one of the reasons that this conference is kind of so important, is because a typical thing when you're working in the planetary science field is you kind of get focused on one planetary body or one particular process, and you just sort of learn all about that, but only within its own context. And I think bringing people together who have looked at the brines on Ceres, looked at the brines on Mars, thought about the brines on Europa or Enceladus, and getting them all in the same room and talking to each other and saying, what do we see in this type of environment? What's going to be important? What are the things to look out for? I think that's a huge part of why this conference was such a great idea.
And I will add that we are getting better at modeling extreme environments. So from theory, including simulation of climate of the whole planets. So it is important to anticipate from this theory if these environments could be short or long duration habitats, what places are good to explore. So there's still many things from experimental to theoretical work that we need to do. And here's an example, but we need as many examples as possible.
So we got to go explore them all, right? The planets are just Pokemon. You got to catch them all.
Well, thank you for that, Ed. And so I want to ask. I want to ask a question for everyone on the panel, and just kind of think about it for now. And this is a question that we'll wrap up with here in a bit. So I ask this question, then we'll go back to our audience questions. So, given everything you heard this week, what is one thing that you will take away that will really impact your research moving forward, or affect, or you may now integrate more into your research moving forward? So just think about that, and we'll ask maybe another question or two here from the audience, and then we'll come back before we wrap up. Okay. Have any of you found good presentations/studies between analog brine systems here on Earth that inform our exoplanet brine systems?
Our local exoplanet expert is
Wait. What was the question again?
Okay, I'll ask it again. Has anyone found good presentations or studies between analog brine systems here on Earth that inform on exoplanet brine systems?
Unfortunately, not at all, because we don't know that much of exoplanets. You have seen a lot of pictures of exoplanet discoveries, but they are all just artistic representations. We only know their size, their orbit, maybe the size and the mass and their orbit, and we don't even know their atmosphere. We don't even know their surface properties or how much water they have, to even thinking about brines. So we can do a lot of modeling, and that's part of the general circulation models that are being used to study possibilities at large, including oceans, salty oceans, and how might that affect the interpretation of the magnetic fields of planets. But this is all still in theory. So our best bet is to get to understand first our bodies in our solar system, and we might be understanding in the process better planets in other stars. But eventually, there is a transition, because we have been detecting exoplanets since the 90s, And now we are moving to understanding the atmosphere. So we will have the capability in this decade to sample the atmosphere, or at least of the smaller planet, because we have been doing that for bigger planets, for the Earth-sized planet in the habitable zone. And then in probably 20, 30 years, we will have some information about the surface properties, about how much ocean they have. But that's still a long shot to understand these systems.
So Abel, actually, as a follow-up question, since you're our local exoplanet person, the Drake equation is often used in the media as trying to estimate how many habitable worlds there are outside of our own solar system. But like you just mentioned, it only really considers, if a body is in that habitable zone, so something close enough to the star that it's able to actually have liquid water on its surface. But as we're discovering in our own solar system, the icy moons of the gas giants, which are definitely not in the habitable zone, might themselves be habitable, right? We have all the nice conditions within these oceans that might actually allow life as we know it to exist inside there. So how do you think that the knowledge that we're learning in our own solar system impacts that Drake equation, impacts what we can start predicting about exoplanet habitability?
Well, there is a general confusion about the term, the habitable zone. You can consider the habitable zone in general terms. I mean, a place where there are some conditions to be habitable. But when astronomers say habitable zone, they mean one particular regarding the orbit or circumstellar or stellar habitable zone. But you can talk about habitable zones at planetary scales, at astronomical or stellar scale, or even galactic scale. What will be the region among the stars to have this star with good planets for life? And in this process, we have to focus. And right now, when the Drake equation is used for the habitable zone in terms of astronomy around a star. If we add and consider the possibility that we see in our solar system, possibility of or planetary habitable zone at any scale, from the atmospheres of planet, even suggesting life on Venus, to going to these ocean bodies in our solar system, then we might have a lot of habitats. But probably those habitats are only good for microbial life. So mostly in terms of the astronomy habitable zone is for surface properties, good for life in general, and more importantly, detectable from space. So you can think about all these possible environments, but if they're surface environment, well, that will take a much longer just to get any idea what's happening below a surface. Even now, we don't have anything about the surface. So that's what the problem is. It's a practical thing just to consider just the habitable zone in the astronomical term right now, but there is plenty of place to explore.
Awesome, thank you. Back to you, Andy.
Well, thank you, Ed. So we're coming near to the end of our time. So I want to thank everyone who's joined us this evening to watch. Thank you for your questions. And thank you to all of our panelists again. But before we go, I want to go back to that last question that I brought up a little bit ago. So moving forward, after the close of this meeting, how do you see what you learned this week impacting or influencing your research moving forward? Let's start with Jen.
That's a really tough question because all of it, all of it will impact my research. I'm going to be following all of these studies, and I think in particular for my research, some of the studies on deliquescence and the stability as well as detection with the Raman and things like that will be really interesting. I guess in a very general term, I think one of the really amazing parts about this conference was getting to know the other scientists and the networking. And now I talked about potential collaborations with some of those people. And so that's the most direct effect that this conference will have on my research.
Great. Yes, the human element. Very, very important. Very important. Sean, how about you?
For me, it's really an appreciation of the complexities inherent in brines. The ability to look at two different areas where we know there's maybe two different brines on the surface and say, okay, what do we see? How do these have different impacts on the geology? I think that really opens up a lot of really interesting questions to look at strange areas of geology that kind of got a little bit brushed over prior to this. So I think, yeah, definitely a greater appreciation for how complicated brine processes can be and just how they can really add to our understanding.
Thank you, Sean. Kennda.
I'll say ditto to both. I'm just trying to think of what else to add. I know for me, you know, all of it it's gonna be great. I'm gonna be following all these studies. A lot of the very specific brine work with microbes and their looking at their ability to survive in different environments. And there was a lot of really great genomic work that has been done that I know for me specifically, as that work comes out, I'm going to be taking that away to help us better understand the microbes that we're trying to understand in the analog environments we work in. So I'm going to be really excited to see kind of the data that comes out from studying these microbes specifically and understanding their processes in the laboratory environment so we can apply it in the field. So I know that that's probably one of the biggest things I will take away, but everything was so useful. It was probably one of the most useful weeks so far conference-wise I've had in a while. So it was great.
Thank you, Kennda. Mohit.
So I think just as important as the things we talked about are the things that we didn't talk about and that are maybe gaps in our knowledge and that we can think about going forward. So we talked about the potential for brines to preserve microorganisms and DNA and biosignatures. But I've been thinking about whether fluid inclusions in salts, so brines in salts, can also trap other things that may be of interest for those of us studying planet formation. And so, for example, noble gases are something we didn't talk about, but are noble gases easily preserved in fluid inclusions within brines? I don't know what the answer is. I think there's maybe some limited research out there, but we haven't thought about that very much, I think. And for nerds like us, sort of studying how these planetary bodies form, I think this will be something of interest in the future.
Great, thank you. Abel.
I think I love exoplanets, but I think that the key to understand life elsewhere are probably in our solar system for different reasons, and especially because we can take those samples back in the laboratory in the near future. And the issue is that our planet, all habitable environments by our standard have life, but we don't know if that's true elsewhere. So it could be as simple as going to Mars or an ocean or explore one of those brines that are supposed to stretch the capacity on environment to support life or preserve life. And imagine that we explore those environments, hoping to detect life, but we don't find any life at all. Even that those environments are now or were in the past habitable by our standards. I think that will be a more profound discovery that even that we have in our solar system transfer of material from the different planets. So probably something from Earth went elsewhere. Still, we don't find that life is common in our system. So probably means that life is more difficult than we think. And maybe we are exploring exoplanets, but the chances are getting indicator for life, it might be worse than we might expect.
All right, thank you. And we'll finish this up with Ed.
Yay! So I think the biggest part that affects my own research is all the mission and the exploration. So my type of research really goes into looking at the data that we're getting back from all of these different places and tying it together with what we know from Earth. So getting to learn about the ongoing missions on Mars, like MSL Curiosity, Mars 2020, and all of the data that they yet have to collect that will let us know a lot more about ancient brines on Mars and potentially even present day. Talking about missions that were already in development and are about to send out, like the Europa Clipper that's going to go to Europa and explore that ocean world and see what more we can learn about its potential inside. You know, is there going to be a kraken that comes out and waves at us? All the way down to missions that we are now discussing and developing and thinking of proposing, like going to Ceres, a world that we thought would have been completely dry and boring, but we get there and it's super cool. And this mission is proposing to actually grab a sample and bring it back so we can study it here on Earth. So all of that awesome exploration that is yet to come, that is the best part.
Indeed, and a nice way to wrap this up. So thank you again to our panelists, and thank you all for watching us online. Hope you all have a good evening.
Adios.